Good evening, students. Let us start with the next topic, which is p-n junction diode. So what do you basically understand with the p-n junction? When p-type semiconductor and n-type semiconductor are formed together, they meet at a point, and that meeting point is known as a junction, and that is known as the p-n junction. When p-type semiconductor and n-type semiconductor, when they meet at the junction, they form the p-n junction. Now, what is p-n junction diode? When a crystal is so formed that half of the crystal is p-type semiconductor, half of the crystal is the n-type semiconductor, then the crystals were formed is the p-n junction diode. So, the two processes which occur in this type of diode crystal are diffusion and drift. These are the two processes which occur. So what will happen when I will join my p-type semiconductor with the n-type semiconductor? As we already know that the p-type semiconductor will be having the excess of positive charges and the minimum of the or very less quantity of the electrons, which are the negative charges, and the n-type semiconductor will have the abundance of the negative charges and very few of them will be the positive charges. So what will happen? These negative charges will get attracted to these positive charges, and the positive charges of the p-type semiconductor will get attracted to the electrons of the n-type semiconductor. So they will start moving from this region to this region, and these electrons will start moving from p region to the n region. So the diffusion will take place. So this is known as a diffusion, and they will constitute a current which is known as a diffusion current. They will constitute a current which is known as a diffusion current. So my electrons will move from n region to p region. They will recombine with the positive charges with the holes of the p-type semiconductor. Similarly, my holes will move from p-type semiconductor to n-type semiconductor, and they will also get attracted towards it, and they will also be able to recombine. They are in the process of recombination. So the movement of electron, the movement of charges will form the diffusion current. So it will form the diffusion current. So the movement of electrons from n region to the positive region will form diffusion electron current, and that current will be with the help of the electrons, and some of the current will be with the help of these positive charges. Okay, so it forms a diffusion. So the process which is being involved over here is the diffusion. So what will happen? Firstly, this region electron will be all shifted to this region, and so they will make a space over here. And when this region of electrons shifted to this region, then we come to this region. So similarly, the region gets wider and wider, and it stops at a time. When the diffusion current stops. A time comes when the layer becomes so wide that the electrons are not able to transfer from this region to that region, and at that moment my diffusion current stops. So here I have shown my layer over here. Here I have shown my layer. So a diffusion layer, and also we know that the net positive charge of p-type semiconductor and n-type semiconductor is 0. Net positive charge is 0. So the point to be noted over here is net positive charges are 0. Net charges of p-type and n-type are 0. Okay. So it comes a stage. A stage comes when my depletion layer gets wider and wider, and it gets so wide that now my electrons are not able to move from the n region to the p region. Also my holes are not able to move from P region to the N region, although they are attracted by the opposite charges, okay, but they are not able to move because this region have now been attained. So stage has come, the region has been attained, and so that's why this region is known as the depletion region or the depletion layer. A layer is formed, that is layer is known as depletion layer, and this layer is devoid of the charge carriers. This layer is devoid of the charge carriers. It will not have any charge carriers. So as we already know that the net charges of P and N type are semiconductors are 0. So if I remove from this N type semiconductor the electrons, because already the electrons have moved towards the P region, so in order to balance that semiconductor, in order to balance that region, the positive charges gets attained over here with around the wall of this depletion layer, around the wall of this depletion layer. And also the because P type is the net P type is neutral, means it is having net charges 0. So P type is having positive charges. The positive charges have been shifted over here. So in order to balance it, a layer of negative charges get surrounded towards this depletion layer, towards this depletion region, gets surrounded towards this depletion region, and these charges start acting like a fictitious battery, and they start acting like a fictitious battery. Now so my EMF is generated in this, which is given by E, which is being given by over here E, denoted by E. Now if any of the electrons wants to jump from this region to this region, it is not able to jump from this region to this region because it is having a potential barrier over here. It is having a potential barrier. Actually, V is given by E into R. Let us say this is the R distance, or D. You can write it as D. E into D. Let us say the depletion region is of the width D. It is of the width D. So it is having the E into D. So potential, how much it has to cross the potential of E into D. And also we know that from bringing one charge to another charge, it has to do some work. What is potential? Electric potential is defined as the work done in bringing a unit positive charge from one place to another place, or from bringing from infinity to that point, any of the point. Okay, so now it has to do some work done, and that work done is also given by charges have to do work done. So now it has to travel this potential barrier. So it is not able to now travel from this region to this region because it is not having so much of strength. It is not having so much of strength. If it would have got the strength to overcome this potential, which is given by V is equals to E into D, then it would have surely been traveled from this region to this region. Similarly, the holes are also not having so much of strength to travel this much potential, the potential E into D, because these charges are acting as a battery and they are having a EMF E, so the potential is E into D, and this, if we consider the distance to D over here, so these holes are also now not having so much of strength to travel from P region to N region. So that's why this is known as the potential barrier for this diode. So that's why this region is known as the potential barrier for this diode. So it is known as potential barrier. Okay, now let us draw the graph also, graph of the potential barrier. So in order to move electron from here to here, what will be the direction of the electron? The direction of the electron is always opposite to that of the EMF E, and or the voltage, you can say, the field, electric field. The direction is always the opposite of that of the electric field, and of the positive charge, the direction of the positive charge is in the same direction of the electric field. So if this wants to move over here, but the direction is will be opposite to this field, so it will not be able to move over there. Okay, similarly this electron, this hole, if it wants to move it will be in the direction of the force will be applied in the direction of this, so this will be in this direction only. So it has to move there, but the direction which is the force which is being applied to this hole is opposite. So again it will not be able to move in this region. Similarly the electron's direction is always given opposite to that of the electric field. So the opposite of that electric field will be direction this way, but the electron has to move from N region to this region, so again it will not be able to move. So this is another way of understanding why the electrons are not moving from one region to another region, and also holes are not moving from one region to another region, and why the diffusion is being stopped, okay. So it acts as a potential barrier. Okay, we have seen till now over here. Okay, the next concept comes of the gradient, potential gradient. We will draw the graph over here. So naturally, the potential, if we draw the graph over here, let us see if we to draw the graph over there here. So the potential of the holes will be greater. The potential of the whole positive charge will be greater. The positive charge is considered to be the greater. So I have drawn over here, and that of electron, the potential of the electron will be less. So I have drawn over here. Negative charges over here, and if we join it, it forms the potential gradient. So this forms my potential gradient. And this is my barrier, potential barrier. Okay, this is my potential barrier, and this is my potential gradient. Now the another concept which is being left over here is the drift. It is the drift current and the drift, hole drift and the electron drift. Now what is electron drift and the hole drift? We have already seen the diffusion. Diffusion, when we join together, the diffusion takes place. Now the drift. Now in this p-type, some of the electrons are there. So these electrons can constitute the current, because the electron direction is always to the opposite of that of the negative of the electric field. Electron direction is of the opposite to that of the electric field. The force which will be applied to over here will be such that the direction of that force will be opposite to that of the electric field. Okay, so electron will easily move. Okay, so electron will easily move. So electron will easily move. This electron can easily move to these electrons are minority charges to the p-type semiconductor, so they can easily move to this n-type semiconductor, and so these will constitute a current. That current is known as the electron drift current. That current is known as electron drift current. The current which is constituted by the minority charges, and similarly over here, the minority charges are the positive holes. So this hole can easily move from here to here. These holes can easily move from here to here, and so they will constitute a very minute current. That minute current is known as hole drift current. So if we consider the majority charges, like over here, The current which was constituted by the majority charges is known as the diffusion current, and the current which is constituted by the minority charges is considered to be as the drift current, and is considered to be as the drift current. Okay, so we have understood now what is p-n junction diode. A p-n junction diode is a diode which is formed with the half of the material as a p-type semiconductor and another half of the material as the n-type semiconductor. When both are joined together, diffusion current starts, and current starts flowing because the electrons, the holes, the positive charges, and the electrons, the negative charges, they both diffuse from one region to another region, and the current starts flowing. Okay, then because of this movement of the electrons only, a depletion layer is created. The depletion layer acts as a depletion layer acts as a potential barrier because it is devoid of the charge carriers. It is devoid, and it does not allow any further movement of the electrons. At this stage, the diffusion stops. At this stage, the diffusion stops. So potential barrier is the barrier because it is providing a potential barrier, because V is equals to E into D. So my E is the EMF which is being found out with the fictitious battery, which implies the fictitious battery EMF. Then D is the distance, so V forms a potential, so barrier. It forms actually a wall in front of these, with wall which is constituted of the voltage. It actually forms a wall, so my negative charges will not be able to move from N region to the P region. Also my holes will not be able to move from the P region to the N region, so it forms a potential barrier. So the potential of the positive will be more, positive charges will be more, since the positive is over here. So I have shown the potential over here. Naturally the positive charge is more, and the negative charges will be the less. So I have shown over here, and so this will join from here to here, and then we will be getting a potential barrier. This represents a potential barrier, and this represents the potential gradient. Okay, thank you. Please share my video, please subscribe my channel, and if you have any doubt, you can ask me in the comment section. Thank you.